Have you ever wondered why some things happen in a flash while others take forever? An explosion is a super fast chemical reaction. Rusting, on the other hand, is a super slow one. This is all about something chemists call the rate of reaction. Think of it like the speed of a car. A car's speed tells you how far it travels in a certain amount of time. In the same way, the rate of a chemical reaction tells us how quickly the things we start with, called reactants, turn into new things, called products. It's the speed of chemistry in action. Science is cool. So, how do we measure this chemical speed? It's all about tracking change over time. We can watch for something to appear or disappear. For instance, if a reaction produces a gas, we can measure how much gas is made every minute. Or if a reaction involves a color change, we can track how quickly the new color shows up. Sometimes a solid might form in a liquid, and we can measure how fast the mixture becomes cloudy. By measuring these changes, scientists can put a number on the reaction speed, helping us understand exactly what is happening in the chemical world around us. Let's consider this. When you drop an antacid tablet into a glass of water, you see it fizz away. The fizzing is carbon dioxide gas being produced. The speed at which those bubbles are created is the rate of that reaction. If you wanted to measure it, you could time how long it takes for the entire tablet to dissolve completely. This gives you a good idea of its reaction rate. Is it fast? Is it slow? By observing and measuring, we can start to unlock the secrets behind why some chemical changes are sprinters and others are marathon runners, taking their sweet time to get to the finish line. Understanding this rate is incredibly important. It's not just for scientists in a lab wearing white coats and goggles. It's for everyone. The rate of reactions affects everything from how we cook our food to how our own bodies work. The chemical reactions that digest your lunch have a certain speed. The reactions that make plastics or medicines in big factories are all carefully controlled to happen at just the right pace. Knowing what makes reactions speed up or slow down gives us the power to control them, which is a massive deal for technology, health, and our everyday lives. Now, for any chemical reaction to happen, the tiny particles involved, atoms, ions, or molecules, have to do something very important. They have to bump into each other. This idea is called collision theory. It's a bit like playing billiards. The balls have to hit each other for anything interesting to happen. In chemistry, these reactant particles are zipping around all over the place. For them to transform into new products, they must first collide. No collision, no reaction. It's the first rule of chemical change, a fundamental principle that governs everything that happens at the molecular level. It's that simple and that powerful. But wait, there's more. Just bumping into each other isn't always enough. Imagine two cars just gently tapping bumpers in a car park. Not much happens, right? But a high-speed crash, that causes a lot of change. It's the same with chemical particles. They need to collide with enough energy to break their old chemical bonds so new ones can form. This minimum amount of energy needed for a reaction to start is called the activation energy. It's like the push you need to get a swing going. Without enough energy in the collision, the particles just bounce off each other, unchanged. On top of needing enough energy, the particles also have to collide in the right direction. They need to be facing the correct way. Think of it like a key fitting into a lock. You can push the key at the lock with all your might, but if it's upside down or sideways, it won't go in, and the lock won't open. Chemical particles have specific shapes and active parts. For a reaction to occur, these specific parts must come into contact during the collision. This is called the correct orientation. So a successful product-forming collision needs both enough energy and the right alignment. So let's put it all together. The rate of a reaction depends on how many successful collisions happen in a certain amount of time. Anything that increases the number of these effective collisions with enough activation energy and the correct orientation, will speed up the reaction, and anything that decreases them will slow it down. This simple idea of collision theory is the key to understanding all the factors that we can tweak and control to change the speed of a chemical reaction, from cooking an egg to launching a rocket into space. It's all about making more successful bumps happen more often. One of the easiest ways to change a reaction's speed is by changing the temperature. When you heat things up, you give the particles more energy. This makes them zip around much faster, like kids after a bit of sugar. Because they are moving faster, they collide with each other more often, but more importantly, when they do collide, they hit with more force. This means a much higher percentage of the collisions will have enough energy to overcome that activation energy barrier. That's why we cook food on a hot stove. The heat speeds up the chemical reactions that make our food tasty and safe to eat. Another big factor is concentration. Concentration is all about how much stuff is packed into a certain space. Imagine you're in an empty room. You could run around all day and not bump into anyone, but if that room is crowded with people, you're going to be bumping into others constantly. It's the same for chemical particles. If you increase the concentration of the reactants in a solution, you are packing more particles into the same volume. This means they are much more likely to collide, which increases the rate of reaction. For gases, increasing the pressure does the same thing. It squishes the gas particles closer together, leading to more frequent collisions. Now let's talk about surface area. This is a big one, especially for reactions involving a solid. Imagine you have a big block of wood and you want to burn it. It will burn, but it might take a while. Now what if you chop that big block into tiny little wood chips or even sawdust? It would go up in flames in a flash. By grinding a solid into a powder, you dramatically increase its surface area. This means there are way more particles on the surface exposed and ready to react. More exposed particles mean more places for collisions to happen, which makes the reaction go much, much faster. Finally, the very nature of the reactants themselves plays a huge role. Some substances are just naturally more reactive than others. Think about the difference between sodium and iron. If you drop a piece of sodium in water, it reacts violently and instantly. It's incredibly reactive. But a piece of iron, it will sit in water for ages before it slowly starts to rust. This difference comes down to their chemical makeup, how their atoms are arranged, and how easily they can break their existing bonds and form new ones. Some substances have a low activation energy and react easily, while others need a massive energy boost to get going. Sometimes we need a reaction to go faster, but we can't just keep cranking up the temperature or pressure. That can be expensive or even dangerous. This is where catalysts come in. A catalyst is a substance that speeds up a chemical reaction without getting used up in the process. Think of it like a chemical matchmaker. It brings the reactant particles together, helps them react by lowering the activation energy, and then lets them go on their way as new products, ready to do it all over again. It provides an alternative, easier pathway for the reaction to follow, a shortcut over the energy mountain. You can find catalysts everywhere, even inside your own body. The catalysts in living things are called enzymes. Your body is full of thousands of different enzymes, and each one is designed to speed up a specific chemical reaction. For example, enzymes in your saliva start breaking down starches the moment you eat a piece of bread. Without these biological catalysts, the reactions needed to digest your food, build your cells and give you energy would be far too slow to keep you alive. Enzymes are nature's super efficient speedsters, making life itself possible at normal body temperature. Industry also relies heavily on catalysts. Making everything from plastics to fertilizers involves chemical reactions that would naturally be too slow or require too much energy to be practical. For example, the Haber-Bosch process, which makes ammonia for fertilizers that help grow our food, uses an iron catalyst. This allows the reaction to happen at a lower temperature and pressure, saving enormous amounts of energy and money. Catalytic converters in cars are another great example. They use catalysts like platinum and rhodium to quickly change harmful exhaust pollutants into safer gases like carbon dioxide and water. So you see, understanding and controlling reaction rates is a massive part of our world. It's not just some abstract idea in a textbook. It's fundamental to industry, allowing us to make useful products efficiently and cleanly. It's crucial for medicine, where we design drugs that can speed up or slow down specific reactions in the body to treat diseases. And it's important for the environment, helping us to break down pollutants. By learning the secrets of chemistry's hidden speedsters, we gain the power to shape our world for the better. Now that's science.